When we design a filter, we need to pay attention to both phase and magnitude. So now we also need to think about the desired magnitude, A of capital omega, of our filter. So often one or multiple pass bands are desirable, where the signal is passed and hence has close to 0 dB attenuation, together with one or multiple stop bands at which frequencies the signal is stopped, meaning that it has strong attenuation. To do that, we need to decide where the band edges are in normalized frequency. So the filter coefficients of an FIR filter, the finite impulse response filter, are its impulse response. So we can obtain the ideal impulse response of a desired filter design in the frequency domain by applying the inverse dt of t to it. The thing is that an ideal filter in general is infinitely long. It goes into the past and in the future, and it's not realizable. So what we can do is that we can approximate our desired frequency response by minimizing, for example, some error functions that which we need to define according to our application requirements. Yeah? Since we have no ideal filters, first we need to give the system some transition bands between the pass bands and the stop bands to give the filter space to come from one state, the passing state, to another state, the stopping state. So this means there need to be gaps between the pass band and the stop bands.